Welcome to our lecture on the continental drift theory. When we look out at the world, the ground beneath our feet feels permanent and unmoving. But what if I told you that the continents are actually on a slow, endless journey across the globe? Today, we're going to explore how this massive geological process works, and more importantly for us, how it has profoundly shaped the diversity and distribution of animal life on our planet. Let us dive in. To begin our journey, imagine you are looking at a world map. Have you ever noticed something peculiar about the coastlines of South America and Africa? They look exactly like two giant puzzle pieces. If you could slide them across the Atlantic Ocean, they would fit together almost perfectly. This simple visual observation is the foundation of a mind-blowing scientific concept. It tells us that the solid ground we stand on is not actually fixed in place. Instead, it is constantly, albeit very slowly, moving. Just like ice cubes floating and bumping into each other in a glass of water, the massive land masses of our planet are drifting across the surface of the Earth. Now that we have a visual intuition, let us look at the formal science. The continental drift theory was proposed by the German meteorologist Alfred Wegener in the year 1912. He hypothesized that all of the continents on Earth were once joined together in a single massive supercontinent known as Pangaea. This massive landmass existed about 300 million years ago. Over millions of years, Pangaea fractured, and the resulting pieces slowly drifted apart to form the continents in their present-day locations. Although Wegener could not explain the exact mechanism driving this movement at the time, his groundbreaking theory laid the crucial foundation for the modern science of plate tectonics. You might be wondering, how did Wegener convince anyone that continents move? He supported his theory with compelling physical evidence. First, he found matching rock formations on coastlines that are now separated by vast oceans. Second, and very importantly for biology, identical fossilized plants and animals were discovered on widely separated continents. Finally, he found evidence of ancient climates, such as glacial scars in tropical regions, that did not match their current latitudes. All of these clues pointed to one logical conclusion: the continents themselves had moved. This evidence was impossible to ignore and demanded a new understanding of our planet. So, why is a geological theory so important for us as zoologists? Understanding continental drift is absolutely essential for studying the diversity of chordates and zoogeography. It perfectly explains why we find fossils of the exact same ancient freshwater reptile, like the Mesosaurus, in both Brazil and South Africa today. Without this theory, the unique distribution of living animals, such as why marsupials are predominantly found in Australia, would be a complete unsolvable mystery. It shows us that the evolutionary history of life on Earth is deeply tied to the geological history of the planet itself. When land masses moved, ancient animal populations were separated, leading to the evolution of entirely new species in isolation. Before we move on to the mathematics, let us see this with a concrete visual example. On the screen, you are looking at a comparison of Earth 300 million years ago versus today. On the left, you see the supercontinent Pangaea. Notice how South America and Africa are snugly joined. The shaded band across them represents the region where Mesosaurus fossils are found. On the right, you see our modern globe, with the Atlantic Ocean separating those same continents. The fossil range is now broken in half. This diagram beautifully illustrates how a continuous animal population was split apart by the shifting tectonic plates, perfectly explaining the scattered fossil record we find today. Now that we understand the biological impact, let us look at how we measure this movement. While continental drift is a geological and biological concept, we can understand its mechanics using a very simple physics equation. The formula is V equals d divided by t. Here, V represents the velocity, or the average rate of continental drift, usually measured in centimeters per year. The variable d represents the total distance the continent has moved. Finally, t represents the total time over which this movement occurred, usually measured in millions of years. If the distance increases while the time remains the same, the continent must have drifted at a higher velocity. Conversely, because the drift rate is so small, it takes a massive amount of time to cover any significant distance. Let us apply this formula to a real-world scenario. Imagine the coastlines of South America and Africa are currently separated by a distance of 4,500 kilometers. Geological evidence suggests they are drifting apart at an average rate of 3 centimeters per year. We want to find out how many years ago they began to separate. First, we must ensure our units match. We convert 4,500 kilometers into centimeters by multiplying by 100,000, giving us 450 million centimeters. Next, we rearrange our formula to solve for time, which gives us t equals d divided by v. We divide the total distance by the drift rate of 3 centimeters per year. This yields a final answer of 150 million years. This staggering number highlights the incredibly slow nature of geological processes. So we have calculated that the separation took 150 million years. This brings us to a beautiful intersection of physics and biology. What does this number actually prove? 150 million years ago places the initial breakup of these continents squarely during the Mesozoic era. When we look at the fossil record, we see that animals on South America and Africa began evolving independently into distinct species at that exact same time in history. The mathematical proof we just arrived perfectly supports the biological evidence found in the ground. It confirms that the timeline of tectonic movement matches the timeline of animal evolution. Now that we have used the formula to look into the past, let us understand how to look into the future. By simply rearranging our fundamental equation, we get d equals v times t. In this form, d represents the future distance a continent will travel. The variable v is the current velocity of the tectonic plate, and t is the projected time into the future we want to analyze. If we assume the current rate of movement remains constant, this equation allows us to project geological changes millions of years before they happen. Let us see how this works with a modern example. Before we conclude, let us see this new formula in action. Australia is currently drifting northward toward Asia at a relatively fast rate of 7 centimeters per year. We want to know how much closer it will be in 50 million years. We are given the velocity and the time, and we need to find the distance. We multiply the drift rate of 7 centimeters per year by 50 million years. This gives us a raw distance of 350 million centimeters. Because centimeters are too small to comprehend on a global scale, we divide by 100,000 to convert it back into kilometers. The final answer is 3,500 kilometers. Australia will move significantly further north. So we have proven that Australia will move 3,500 kilometers. This brings us to a critical realization about the future of life on Earth. This massive geographical shift is not just a change in coordinates. Moving that far north will drastically alter global ocean currents and local climate patterns on the continent. Consequently, the future evolutionary paths of the animals living there will be forced to change as they adapt to these new environments. This proves that zoo geography is not just a history lesson. It is an ongoing, dynamic process, and continental drift continues to be a primary driver of evolution today.
To wrap up our lecture, let us review the most important ideas we have covered. First, the continental drift theory fundamentally changed our view of the Earth, proving it is a dynamic, ever-changing system rather than a static rock. Second, this geological movement is the key to making sense of the scattered fossil record, explaining why closely related animals are found across vast oceans today. Third, the shifting of these massive land masses has been a primary driver of evolution, forcing species to adapt or evolve in complete isolation. Finally, we saw how simple physics allows us to calculate these massive changes across millions of years. You now have a solid understanding of how the moving Earth shapes the tree of life.